with that introduction, I think I'm going to hand it over to Matt. Matt runs product management for us. And Matt's here to give you a little preview of some of the product announcements that we're going to be rolling out to the rest of the world next month.
Great, thanks. Dave. So I'm going to jump right in for sake of time, and first I'll cover where we are on the agenda. So I'm going to talk about photonic agility. We talk about DevOps control. Photonic agility is kind of what we do. I'm going to cover the photonic agility part, and really it's about some new hardware that we have coming. So I'm going to tell you about some new hardware and a little bit more new hardware. And I'm going to wrap by telling you why that new hardware is important in the context of all this stuff. I'm not going to tell you that ahead of time. So you're going to see a lot of boxes and things like that. I hope you don't get confused by it, but we'll bring it all back together at the end. Really what we want to get to is Toad and Simon to show how this is all controlled via our DevOps integration. And we'll have a few demos on that side. So I want to save most of the time for that, so apologies if I go fast. I'm going to start with something that we call the Plexi pod switch interconnect. And this might be new for some folks that have some familiarity with Plexi, and hope this makes sense to everyone. So if you haven't seen this before, this is kind of our reference architecture. And we really like to kind of be up here in terms of understanding how to build affinities through, in our view, kind of the whole DevOps mantra of kind of going very quickly from development to operations. Doesn't really end until the scaffolding that binds applications together is imprinted in the network fabric itself. And all that information of how that scaffolding, what it is and how it's built, is a lot of that intelligence already being put into lots of tools, into your orchestration layer, and things that we see around the data center. So a lot of what we do today, and a lot of what you'll see from Toad and Simon, is around how we get that information and what we do with it to understand what needs to be built underneath it. Everything kind of below this kind of red circle is kind of the photonically agile layer, right? And we built that because we had to. We wanted ways to actually free the wires. We wanted to be able to, once we understood what that imprinting needed to look like, we wanted to be able to imprint it in a way that was dynamic, not fixed in wiring. So we talked to you previously about our Plexi switch fabric, which is, as Dave mentioned, kind of a simple 2-degree ring architecture. And really our goal is to allow customers to put those, that photonic layer together any way that they want to, right? We've talked about rings in the past, but some customers may not like rings for whatever reason. So we came up with, in addition to our product line called the Plexi PSI, stands for the Pod Switch Interconnect, and this is primarily for customers that are building scale-out data centers built on kind of uniform pod architectures, where generally every rack and every row is built very similar, and we'll talk a lot more about this. So, what does this look like physically? Instead of our switches being cabled together in a ring, they're cabled in essentially what looks like a hub and spoke topology. So we've got edge switches. These are Plexi switches, and you'll notice these kind of look like 2U switches. So I'm going to cover those in a little bit. This is kind of built on some of the new platforms we have coming out. But basically this is an Ethernet switch with optical uplinks. And I'll tell you in detail kind of how this is cabled and all that. But these are basically what it looks like is an edge layer of switches in kind of an optical spine layer, for lack of a better term.
It looks like a token ring Mao.
Yes.
Call what you want. It's not.
I know.
So, and I'm going to tell you what this thing is. So forgive me to kind of just skip over that for right now. But again, why did we build this specifically? Because we have customers that want to build pods, and they want to build a block of servers with storage compute in a very uniform way. They want every rack, every row, all these things to look the same. So with this type of architecture, we can kind of pre-build a very kind of uniform model. We have kind of, I'll show you in a bit, we have kind of pre-standard SKUs for this. And they also want to optimize for price per port. So one of the other benefits of this architecture is extremely low price per port. What does the PSI look like in terms of physical components? Well, there's a optical component of this, which is the actual PSI. And this is a completely optical chassis. It's a small 1U box. It's got 12 essentially light rail, as you know, the light rail cables that we have on our switches.
It's a token ring MAU.
We'll go into details and you'll see what it does. So
it has a bypass, it's
Are
passive.
you having flashbacks?
So normally our Plexi switches cable to each other over 2 light rail cables. In this case, they actually cable to the PSI. This model of the PSI has 6 pairs of light rail connectors for switches, so it can connect up to 6 switches. And what it does is internally it implements all the bypass capabilities that we normally have in our ring topology, or our standard topology that we normally have in our ring. So the only thing that's really different is the cabling. From a controller perspective, this actually implements a ring, so it looks like a ring. But all the kind of ringness is actually implemented inside the PSI chassis itself.
Are you dual homing the top of rack into these PSIs? Or?
This is a passive box. You can dual home it. You can build dual fabrics. We'll talk about redundancy in a second. Some of the nice properties of this is, you can add and remove switches here, and it doesn't disrupt anything else in the domain. It maintains all the photonic switching of the Plexi solution. These 3 ports here are extender ports. Those allow us to essentially build, kind of continue to chain these things together. So if you need more than 6 switches, you chain these together and you get another 6. So this is kind of what this looks like. If you want to extend them, you can essentially chain these together over the extender ports. Any number of these can be chained together. So I showed you an edge switch in that first picture, but I didn't tell you what it was. So that was actually what we call the Plexi Switch 2 SP. Notice our former generation of switches were called the Switch 1. This is the Switch 2. So you're going to see a number of different models of the Switch 2 here, and we'll kind of get to at the end kind of the basic architecture of what the Switch 2 is. But I want to talk about this specific configuration first. Essentially it's a 10 gig optimized edge switch, optimized for high density server access. It has the equivalent of 72 10 gig access ports and 3-to-1 oversubscribed. So the way the access ports are comprised is 16 QSFP ports that can be broken out obviously into 10 gigs, and 8 SFP ports. So a total of essentially 72 equivalent access ports. We have something called flex ports, which I'm going to get into detail on later, but keep that in your mind for right now. And then out of the back of these, or essentially, everything's on the back, but we have 2 light rail interfaces, just like we had in the Switch 1. And these 2 light rail interfaces have essentially 12 by 10 gigs carried over each light rail. So
12 lambda going left, 12 lambdas going right.
Yeah.
Okay.
Yeah, exactly. Well, essentially, the way this is wired is they're all going up to the PSI. So it's not really left and right now. It's just all going,
Okay.
Essentially, think about it as having 24 by 10 gigs up to the PSI, just over 2 links. This is using non-WDM optics. So we have standard 1310. It is 1 kilometer, so it's not short reach. It's actually 1 kilometer optics, but standard 1310 optics. So this allows us to get very, basically, fundamentally, this looks very similar to kind of a standard top-of-rack switch, right? It doesn't have the WDM MUX capabilities that we have in kind of the other switches.
So you're effectively running 12 fibers to
Yes.
the PSI.
That's right.
Okay.
Right. On the control plane, we have a quad-core i5 with 8 gig of RAM. So that's our CPU complex. So as I mentioned, this has essentially those 2 light rail cables get hooked into the PSI, and the extender ports allow us to kind of chain those PSIs together. Again, these are 1 kilometer optics, so we can actually still maintain some distance here. The WDM optics that we use in the other products have nominally 10 kilometers reach, in some cases higher. So we broke this out to make this easy for customers. We created these in kind of fixed SKU formats. So when you're building pods, and you don't have to buy in these, but this makes it very easy for customers. So a single pod, for example, might be that first configuration, which is 6 to 12 rack rows. What was it? Essentially 432 10 gig access ports. Which is 6 of those switch to SPs and one PSI, all interconnected. So we would basically sell that as a pre-configured SKU.
So if you go back to the previous slide, the right-hand side, so the extender ports, are still not the DWDM or CW.
That's right. Yep.
So you effectively went back from that neat concept of lambdas back to the concept of individual fibers.
Mm-hmm. Yep. And we'll go back to WDM as well, so we'll show you. Okay. Why? I'll get to that. So this essentially is that one pod configuration: six switch 2 SPs, one PSI, about 432 access ports in that config.
Will you get in how this actually gets wired together?
Yep.
Okay.
A 2-pod config, essentially double that. 12 switch 2 SPs, 2 PSIs, and a 6-pod configuration. So these are kind of pre-built configurations. We have customers that may have variations of this. We can kind of build these in any size, but again, to make it easy, we have these pre-built configurations. When we sell these are all kind of all-inclusive. So all the cabling, all the optics to connect all your switches together, and all the software licensing, all kind of fall under that one SKU.
But by default, to my question earlier, by default, are you trying to package just one PSI in terms of a number of pods? Per pod, is it 1 PSI? Is that your default recommendation?
Yeah. I mean, it's again, it's completely passive. There's no,
But in terms of if that fails, you still lose.
Yeah, any redundancy at all?
You want to talk about? You're not mic'd though.
So you can't be heard.
You're passive, so what can fail?
I mean, look at this, it's a patch panel. It's a smart patch panel where we've done, there's lots of fibers in there. There's close to 500 fibers inside of that box. But we've essentially created a patch panel to create the connectivity between those switches inside of a single box. There's no power, there's no moving parts. It is purely a patch panel, just a smart one.
But still just one panel.
It is still just one panel, right? I mean, how many people have duplicate patch panels is one question. Still, you can actually separate these either by creating 2 rings on top of each other, or you can actually separate the PSIs to have 2 of them redundantly and have one to one and one to the other.
Or Jason, if you have redundant server connectivity, you just build 2 rings.
Yeah. We would do dual.
Right.
Every customer we go to that wants that kind of redundancy, they build 2 rings, right? They build 2 parallel rings, have server connected to one ring and another ring.
Yeah.
There's a picture on Ivan's site that shows the intermesh of the connections really well, and it gels the idea together. Until you draw it out, that's for me, I had to draw it out to get it, but when you get it, it makes a lot of sense. It's really, pretty good.
Yeah, and functionally, if you take these 6 switches and ring them all together like we would do in the switch 1, functionally looks exactly the same, right? The only thing is this passive patch panel that's basically homing all the cables in.
So now with this patch panel and everything, you've effectively created a token ring.
I'm not a token ring expert.
Well, instead of 4 meg, you have 120 gig.
No.
There's no token.
And there's no token. Yeah.
Aside from the fact that there's no token, it looks nothing like Token Ring.
So now you effectively you have point-to-point links between adjacent switches now.
Yes.
Which we had before, right? We had point-to-point.
Well, no, you had those lambdas that were going.
Still has that. That's just all implemented here in physical cabling. So the physical topology of this is still 40 gig between these 2 switches, 20 gig bypasses. All that is still.
Oh, so
exactly
instead of WDM in the switches,
discrete
now
fibers.
you have a fixed sort of matrix in the patch panel.
Right.
Yeah. So, Yvonne, one way to describe this in other terms, there's a couple things that we've done with this. The topology that we manage doesn't actually change. Mm-hmm. What's happened is what used to go in a bypass through the physical ring is now collapsed inside of the PSI.
Yeah.
The only vestige of an actual ring here is just a little part of the control plane. All the data plane is actually fully meshed.
So
every logical backplane link is tracked as a separate connection, and there's liveness detection and dynamic discovery on each backplane link.
But the PSI is wired at whatever fixed topology. So previously, if I would go from 5 nodes to 6 nodes, the topology of the chordal ring would effectively change. So that I would have different. As I would go from 5 to 6, I would lose some bandwidth between any 2 nodes. So the smaller the ring was, the more bandwidth I had between nodes.
Yeah.
And here the topology is fixed, right? So we're always at 6 nodes.
Well, when you chain this together, you have another 6 nodes. So it's just like extending the ring. Right.
If I have only 5 nodes, then some fibers are going nowhere.
That's right. And that's why this is, sorry.
Okay.
So that's why this is actually great for pod deployments where it's very uniform. It's always a certain size. The WDM technology is great for kind of organic growth. You know, I don't know how many I'm going to have in this rack or that rack that may be different, or I might want to continually increase.
Plexi's expectation is you're going to sell this as a pod with all of those components. All of it's going to be wired up and used to maximize the solution.
Exactly.
Yeah. So are they happy with a single switch for top of? They're not looking for multiples.
So I'll get to redundancy in a second.
In this model, you know, can you actually, what would happen with a third-party switch going to PSI, or is there still special, photonics in the top rack switch as well, or is
no? So this could, in theory, be a standard switch.
Right.
You don't get the optical cabling benefits. You'd have to kind of have some type of big breakout cable that takes multiple QSFPs into an MTP, for example. But we couldn't control it unless there's our software, running on that, because it still needs to cooperate as a ring, right? So
the PSI and you probably already said on this that's passive. That's just doing. Is that one-to-one? It's no photonic switching or anything like that.
That's right.
Okay,
It's all.
cool.
It's
Thanks.
literally a bunch of cables.
Gotcha.
So the customers that we have that are building kind of these standard, big build out, they already know what exactly every rack's going to look like, every row's going to look like, and they want it all pre-wired. They can get a lot of cost savings here, and they're kind of familiar with the wiring pattern. So each pod essentially represents a single maintenance domain, just like a ring would. All the switches maintain that fully meshed optical topology, just like before. There's no configuration required for this, so it's it's a completely passive layer, and it is all self-maintaining. So if you pull a switch out, all the bypasses are maintained. All that stuff happens very nicely. So redundancy, certainly you can have fabric redundancy, meaning essentially just like you would build dual rings before, you could build dual PSIs exactly the same way. This showing there the dual fabrics. And the controller redundancy, which we've kind of covered in the past, our controller doesn't have to be in the data path, so if it disappears, everything kind of keeps forwarding. We have support for redundant controllers and synchronous databases. Does that cover your redundancy questions?
Yeah, it seems like if you go the approach, dual NIC server, the middle dual fabrics is what the recommended ideal solution would be. So it's almost like 2 pods, leverage like pod A for fabric A and then pod B for fabric B.
Right.
Yeah.
So again, we've talked about a lot of this in the past. We have a hierarchical control plane, so we've got the kind of the global controller or the central controller that is your kind of interface and does all the global optimization, and then we've got the distributed co-controllers that run on the switch. All of that is exactly the same. The data plane, again, the switch insertion and removal doesn't affect any transit traffic. We get all that meshing, and we do all the optical monitoring on all the paths. So all that stuff is kind of handled kind of behind the scenes. The fast local repair. So the notion that we have a co-controller in each switch allows us to kind of deal with all the local fault issues in real time right at the switch. We don't have to have the controller tell us about how to deal with a fault. So, and that happens even when the controller is disconnected, because all of that information is pre-computed. So what if you want to kind of increase the bandwidth of this? So we've got this kind of pod architecture. Is this? Yeah. So this is our another variant of the Switch 2 called the Switch 2P. So it's built on the same architecture as the one I just showed you, the edge switch. But this one is actually has, instead of the 2 light rails coming out, it has four light rails. This is our 4-degree switch. Again, all using non-WDM optics. So these are all part of kind of the pod architecture. But if you think about this, and just for simplicity, draw kind of a ring, because logically, even the PSI looks like a ring. And if you want to take that ring and add more capacity to it, right, you can kind of have this notion of concentric topologies on top of that, physical topology. So these big blue circles are actually this new switch 2P, which actually can be on that first ring and also create its own separate ring kind of around that with additional capacity on that. So there's essentially now another 240 gig in addition to the others. So there's a total of 480 gig of fabric capacity on this. The trade-off is obviously you have fewer access ports. So this has essentially 48 access ports versus 72 and 48 light rail ports. So this allows us to actually start to add bisectional bandwidth to the architecture by essentially dropping in these switch 2Ps in various parts of the ring. You can also look at it like this. So you've got these different pods with the PSI. So you've got those 6 switches connected to PSI, and you've got a bunch of them. You could add, instead of having 6 switch 2 SPs, you would put a 2P as one of the switches. It acts as an access switch, but it also and it connects to the PSI, but it also allows you to optically ring those pods together. So again, it gives you more L1 capacity. This can be done, in any number of these switches. So the more you add, the more capacity you get. So it's a way to incrementally scale bisectional bandwidth within the pod. So the 2P, again, it's same form factor as the Switch 2 SP, and I'm going to summarize all this at the end. But it's optimized, instead of for edge access, it's optimized for interconnect. So essentially, it's got a 1-to-1 oversubscription. That means it's got 48 10 gig access ports. So previously we had 72. This version has 12 QSFPs, which equates to 48. And then it's got the 48 light rail interfaces. And it also has the equivalent of 4 QSFP and 12 SFP of those flex ports that I told you to remember about. I'm going to tell you about in a second. Same CPU complex. This is actually the same exact switch. The only thing is we've taken some of those access ports and made them into additional fabric capacities over a separate light rail. So kind of to summarize the pod architecture, the goal for the customers in this case was a kind of a hub and spoke wiring pattern where they could build essentially what the customers are doing in a lot of cases is top of rack switches in each of the racks. The middle of the row, they want to wire everything into the middle of the row. So the PSI essentially goes in the middle of the row. And that's a very familiar wiring pattern for them. And they can kind of pre-build those and kind of snap the racks in a very uniform way. It gives them extremely low costs. So we're list pricing this, fully configured at it's going to be under $500 per port list price. And that includes, again, all the cabling between switches, all the optics between switches, all the switch control licensing, and for essentially a 10 gig equivalent access port. So
500 per port includes the optics or not?
All the fabric side optics, yes.
Oh, just the fabric side?
Yes, okay. not server side access SFPs.
Because they're the expensive ones.
I know. That's why I asked.
What's that?
The server side optics are the expensive ones.
You need DAC cables, cheap, but it's a wash when you compare that to if you take standard Arista switch or whatever, and you look at price per port, they don't include any of the optics, right? Because they don't know how it's going to be configured. Ours are always configured. I'm just saying it's important to understand that essentially either 24 or 48 ports equivalent worth of optics and cabling is configured in our.
You've mentioned the cabling a few times. Is that more meaningful than I understand?
They use special cables.
Oh, it's special cables?
Yeah, we use the MTP or MPO is the proper term.
Doesn't sound special to me.
No, they're ribbon cables. They're stock off the shelf. The only reason I mention them is because, again, when we talk about price per port, we're including those in, and that could be a significant cost. If you're just looking at, hey, I can buy a top of rack switch for whatever, dollars per port, it's an empty cage, right? I haven't bought any SFPs for my inner switch connections. I haven't bought any line cards for my chassis spine. I haven't bought any cabling to connect the two.
Sure.
Right? All that is kind of included with us.
So my customers that would be candidates for this kind of a topology all have their favorite cabling vendor and want to use the Corning or whatever product it is they're using, and I think they would throw those cables away if they were included.
We've done things where we net them out of the BOM. If somebody wants to supply them themselves, we provide specs of what it is. The only reason we supply them really is because we did color code them and key them just to make it kind of foolproof to go, in the ring architecture to go east to east and west to west. But we're actually getting rid of the keying, just color coding for ease. But and we're using standard coloring anyway, so you can get that from your vendor anyway. So nothing special there.
So your pitch should really be, if you buy a switch with $500 per port from any other vendor, you will waste half the ports or a third of the ports to build the fabric. And here you're charging $500 per port, per usable port.
Well, the $500 per port is actually per equivalent port, meaning I priced all that in, and I've used that as a denominator as well.
That's per usable user-facing port.
Right.
No.
Yeah.
No. Let's be careful. We use same terminology. $500 a port is all ports, including fabric ports.
Yeah.
Aha. So you
priced it in. We've also included it in the denominator, so it's it's netted out. So when we say,
so it's 500 times 96.
Correct.
Sure. Right.
Aha. Okay.
Includes software and everything else, right? There's nothing
total cost.
Yeah. So the next question: does this mean? So this is obviously not compatible with your previous switch.
You wouldn't build a kind of a ring and a pod kind of and commingle them.
Yeah. So does that mean that you are stepping away from WDM?
I'll show you in a second. We're going to go back to WDM. Okay. Again, going back to, we want to let you make a photonically agile network however you want to do it, right? And if you're building pods, we've gotten feedback from customers that they want to do it this way. So we've given them that option. If you want to build kind of, kind of the rack and roll model, I've got my rack. I just want to clip it into the two adjacent racks. That's a nice kind of organic growth model. So I'm going to get into that now. So we talked about the 2P and the 2SP. Those were kind of the pod variants. That's why the P's in there. Now we're going to talk about the switch 2, which is essentially, again, reference architecture. That's the Plexxi switch 1 fabric that we've talked about in the past. And if you want to take that same model and now grow that with the additional port capacity and the additional light rail capacity of either 2 degree or 4 degree, we do that with the Plexxi switch 2. So we'll start with the kind of edge. So we have two variants of the WDM model, as we had two variants of the pod model. We have the kind of one optimized for edge access, which is again a 72 port access ports with again 2 light rail ports. So conceptually, or exactly, this looks exactly like a switch 1. Which had 48 access ports and 2 light rail ports, except this one has more access ports. It's built again on the Trident 2 chipset, just like the Switch 1X was. But in this case, you're getting additional access density. So if you're looking at kind of in comparison to the Switch 1X. Exactly the same architecturally, exactly the same, the way you build it, more ports. One of the key differences actually here, and I'll talk about this finally, is this notion of flex ports. And you saw that in the other models. And what is a flex port? And I'll actually tell you in a second. so if we look at kind of the architecture of the switch 2 again, this is the same block diagram for all the other switches that were switch 2 based. We've got a packet switching ASIC, which is the Broadcom, which connects directly to a number of access ports. We've got a co-controller CPU complex over there. And then we've got this kind of optical electronic crosspoint switch. So these flex ports actually bypass the actual ASIC switching fabric itself and go directly into this optical crosspoint technology. What does that do? That allows us to basically provide a kind of a layer 1 native access to the light rail. Why would you want to do this? A couple of reasons. One is you might want to just stretch some non-Ethernet transport from the rack across the light rail. Fiber channel, InfiniBand, something that's coming out of the rack, non-Ethernet wise. You could plug into these flex ports. You buy a fiber channel transceiver or an IB transceiver. We map those right onto essentially a lambda, and it spits out on the other side into another switch, and you terminate it on your FC director or whatever. Yep.
Is that wiring from flex ports into lambdas fixed, or is it programmable?
It's programmable.
So you can effectively say flex port 1 on this switch terminates on flex port 3 on that switch.
Yes.
Cool.
Yes. And not only that, but you can also redirect some of these flex ports into the switching ASIC if you need more access ports. You can do the same thing. You can actually use this crosspoint to mirror traffic at layer 1. So if you want to say, OK, this is going to the fabric, but it's also going to mirror out on a port, you can do that as well. All of that is software configurable.
What's the CPU and then the bus? What's the trace going into the packet?
I'm sorry?
The CPU, what's speeds, specs on that?
This is a Core i5, i5, quad core, 8 gig of RAM.
Is it just one trace into the SoC?
Into where?
Into the switch on chip. I assume that's a Broadcom ASIC right there.
Yeah.
So Trident 2 means 3240 gig IOs. So how many do you present to the front, and how many do you present to the flex port?
Depending on the model. So the 2S models, whether it's the 2S or the 2SP, have 72 equivalent out the back and 24 to the fabric, so 96 total. The 2 and the 2P have 48 and 48. So
if you think about this, right? So they're all wired the same, right? And they're wired just like this. Half of them are going to the front panel, half of them are wired to the cross connect. And the various versions that you see with one light rail, multiple light rails, is us manipulating sort of a preset manipulation of that cross point to have some of those light rails show up on the front panel versus on the light rail.
So I could achieve a 1-to-1 contention ratio in the backplane?
Yes.
You could. You absolutely could.
The 2 and the 2P are pre-configured at 48-48, so 1-to-1.
Right.
Did I miss any of the uses of the flex ports? We got the mirroring, we got the stretching non-Ethernet, and additional ports.
Those are the most common ones.
Yep.
Now, mirroring.
Yep.
Can you obviously you can program that?
Yes.
Yes.
Yeah.
It's
so you just reinvented Gigamon.
Yeah. It's these things are capable of doing mirroring in the silicon. At layer 1. So why not? If you want to actually get a trace anywhere. In the future, we could do some more fancy things like, if this is oversubscribed, we could move some of the capacity over to an undersubscribed ASIC. Those are kind of optimizations that we could do in the future.
So for the mirroring, right? There's a slight difference in mirroring in the crosspoint versus mirroring in Trident 2. Right? I mean, in Trident 2, a mirror is a replication of a packet.
I know.
Right? Whereas in the crosspoint, it is a truly optical replication.
It's a passive
so whatever error happens to be on the wire, that error is going to come out your mirror as well.
It's a passive tap.
Yeah. The other use case I didn't mention here is, and this is actually one of the first ones that customers are using, is DCI. So you can actually steal some of these fabric ports off the light rail and have them egress out the chassis on a QSFP or an SFP port, which could be a DWDM SFP, for example. So if you want to actually now extend your ring 60 kilometers, you could Layer 2 DCI, I know you love it. We have customers that want to do that, believe it or not, and they are doing it. So
I believe it.
It's great for the colo market. They like, they've got small, it's actually a relatively small ring, small number of switches per site, but they want them all extended. Essentially, it starts to look like Metro Ethernet. But that's another use case of that. I skipped over some slides here. So fundamentally, the switch 2 and the 2P are multi-dimensional switches for interconnect. Again, two light rail ports. In this case, they're WDM based, so we can create rings of rings, and I'll kind of show you some of that. We can do just like we did with the kind of PSI architectures. You can start to sprinkle these into, if you have a switch 1 complex and you want to increase the bisectional bandwidth, you start to put in drop in switch 2s to kind of give you additional fabric capacity. And let me show you kind of some of the ways that we do. This is kind of again that kind of concentric interconnect capability. So again, these switch 2s sit on essentially both rings. They've got their another 240 gig light rail that connects themselves. They also sit on the other the switch 1 240 degree light rail. This is fully compatible switch 1, switch 2. So we for customers that go ahead.
So one thing to notice here, right? So you've created additional bandwidth, right? Additional paths between big portions of the switch. The controller will actually use these paths, right, to find it. So if you have traffic that needs to be directed from one side of the ring to the other, right, you're going to find one of these switch 2s, jump over a whole bunch of switch 1s to come out the other end. Right, so all of these paths, and this is dynamic, right? The controller has no preconceived notion of what paths exist or don't exist. They're being told by the switches. So in this case, all these paths are simply being presented to the controller, like, here, use it. Right? However you want to fit the traffic on this, I have this additional connectivity between parts of my ring.
So this is really cool, and this is the previous picture was kind of showing you how it's done conceptually. This is actually a little more what it would look like in reality, and we have a lot of customers that are planning for this type of architecture, where essentially you can think of each of those rings as a row, and now you want to ring the rows together. So you put switch 2s on one end or both ends and create a ring around your rows. We have customers that put them in the middle.
Ring around a rosy?
What's that? Ring around the rosy, yeah, exactly.
That'd be a, is that a hypertoroidal fabric then at that point?
Yeah, technically it's a, what do the guys tell me? It's a 2D torus, but physically, but it's actually a flattened butterfly. Right. Anyway, the point here is we talked about this with switch 1. We talked about from a scaling perspective, we have kind of this notion of stacked donuts. In switch 1, you had to kind of connect them electrically. What switch 2 allows us to do is now connect them photonically, right? So we have additional pathways that allow us to create more paths and leverage those paths via the controller.
Is each one of those 16 or so rings a ring of many switches?
Yes.
I see.
Yes. So generally, we see customers in the kind of anywhere from 10 to 30 in kind of a single ring kind of notion, which is generally the size of a rack, right? I mean a row, right? So it fits very nicely for that. They make that a ring, and then they want to go ring the rows together.
Each one of the rings are photonically unique, right? In terms of they're not actually sharing any optical space between that end row switch and the other. Is that getting optically switched?
Yes.
That end row switch into a new ring, right?
Essentially into a new physical ring. Yes, okay. Absolutely. Yep. Okay. Yeah, and all that happens photonically at wherever that junction point is. Okay.
And to go back to the block diagram that was in there, right? That optical cross connect. Now you can see you can actually take a wave in one ring and use that optical cross connect to actually map it onto another ring, right? So you can actually create a layer 1 path, right? In one ring, jump onto a second ring.
Jump onto the second ring and then pass it.
So I can actually create an end-to-end layer 1 path from a switch in the top ring over there to a switch in the bottom ring there without ever touching a physical Ethernet switch.
Okay. I get it.
I'm trying to rush through this because I want Toad and Simon to kind of get their share of time here. So just to kind of summarize, in the WDM line, there's two new models, the 2S and the 2. The 2 is the 48 1-for-1. The 2S is kind of the oversubscribed version of that. So if you want to do additional edge port density, you can do that. And this is just kind of to summarize everything, all the new hardware that we are kind of coming out with in the next month or so is summarized here. So the pod architectures, we've got the 2SP and the 2P and the PSI. And kind of the WDM architecture is the 2S, the 2, and the switch 1. Again, all the 2 models share exactly the same architecture, just different configurations and different optics between those 2 columns.
So you said availability in about the next month. So
yeah, we're going into kind of our trials at the end of October, which is when we'll launch it officially, and then it'll be GA roughly around the end of the year.
What's the price per port on the 2S switches?
2S is it kind of well, let's say it varies. It's if you build a network with all the WDM lines, it's somewhere between $1,000 and $1,500 list price. So somewhere in that range, depending on how much bisectional bandwidth you configure. So depending on how many switch 2s you put in the.
So it's like twice the price of the pod version.
About that, yep. And what we see is kind of a delineation between the customers that are building kind of pod architectures, very optimized cost per port, versus kind of organic growth that are more system price and kind of integration sensitive. So I promised I would kind of summarize why we did this and not leave you in the lurch on why we have all these new hardware things and stuff, and apologize for the ugly slides. But I'll kind of talk through this very quickly. Again, we talk a lot about DevOps controlled photonic agility, and I think that's really what we're trying to kind of bring to the market and kind of talk to the world about. Cooking class is great. Guess I need to learn how to cook. So the workload and workflow metaphor work like this. In the photonic agility, our goal is to create lots of physical paths. Our belief fundamentally is that Dave talked about 2 types of switching, electronic and photonic. Ultimately, in the fullness of time, electronic switching starts to move to the edge of the host of the network. Right? We've got lots of cores. We've got a very capable vSwitch. We've got an interface with virtual networking that is our network virtualization that is very kind of convenient for the end user to kind of think about their network constructs. There is really kind of no reason for us to take all of that edge electronic switching and then just reaggregate it back into a central electronic switched core. So our goal is to create lots of paths and host-to-host, optimize for host-to-host pairings. So all the stuff you saw, 2S, 2P, all that kind of stuff, all built on the same theme. Give you lots of path from edge to edge. Today our edge kind of extends out still to a physical electronic tier. Who knows? Someday that electronic tier may disappear right into the host, right? Maybe in 3 to 5 years, and different host architectures. But once we're in the optical domain, our goal is to leverage, to borrow Yvonne's term from yesterday, robots, right? To maximize those network resources, and that's really the notion of workload optimization. The second big piece of what we want to talk about is DevOps and workflow. To me, workflow is about building context and metadata dynamically. So in order for us to maximize the use of all those paths, we need to have some context. And we need to have some context that's not derived from us building more electrical, looking in packets, doing DPI and that kind of stuff to understand what is what. We want to build context out of band dynamically. And that is through the notion of connectors into the universe of DevOps where that metadata is being built already. And again, I said this at the beginning, our view is that the workload is not, if you take DevOps from development to operations, it's not fully it's not fully operationalized until the network is imprinted. The application inner working requirements, the scaffolding that ties those components together as a delivered application is imprinted on the network fabric. It's not just about, DevOps to us is not just about configuring switches using the same kind of legacy networking terminology. It's about us actually enabling an application with all the things that it requires and operationalizing it. And just to kind of sum up what we believe in, because there's been a lot of debate in the world about overlays and underlays and all those kinds of stuff. I thought it was important to kind of just end with this, and I've already said some of this. Electronic switching is increasingly moving towards the host. Maybe it'll ultimately be in the host. The role of the physical network is, in our perspective, to deliver application workload the scaffolding. optimized around host-to-host pairings, right? So we really need the context to do that, and we really need lots of host-to-host connections. This is really, where we kind of differ from the market is this is the opposite of aggregation. The notion that you can kind of take everything up from large numbers of hosts and into kind of a big electrical complex and process it and discriminate flows is to us the wrong way to do things. We want to keep the fact that we've got lots of hosts that want to communicate with each other, give them lots of ways to do that, and optimize those pairings dynamically. So, leaf spine is perfectly good configuration for, many circumstances. It's got known operational and behavioral characteristics. We also think it can kind of be problematic for diverse workload environments. So, we know this for a fact. We know that as flow scales, the notion that randomization provides load balancing is untrue, right? This has been proven through networking for the last 20 years. There's Google papers on self-similarity and long-range dependence. There's, as your flows scale, burstiness increases, right? You still have hotspots, you still have congestion, and aggregation leads to buffering, leads to latency, and we want to avoid that. And with that, I am going to.
Quick question. So I didn't hear you mention 100 gig. What's the optical life cycle on the merchant? I assume you're buying off-the-shelf optic on the optical side. When's the next 100 gig rev on that?
100 gig for optical interfaces, for photonic interfaces?
Optical lambdas.
You can get 100 gig today. I mean, the question is, you want 100 gig for, really what we're trying to do is have lots of paths. If we want to aggregate them together, we can do that, but giving us more 10 gig paths is actually just more granularity to leverage those paths. If we start to think about putting everything in a big bundle, then it's harder to break those out and use them more intelligently. Mm-hmm. But certainly the technology exists, and the form factors are getting down, for where 100 gig will probably be feasible in, SFP form factors fairly soon.
Yeah, no, and I'm just kind of curious. I mean, so we got T2 coming up with 100 gig shipping, so.
Yeah, when you look at leaf spine, 100 gig may make sense because you want to kind of aggregate everything up over bigger interfaces and, do things like, aggregate transceivers and, MXP type of things. What we want to do is actually avoid aggregation, so keep things diverse as long as possible. So we're less interested in kind of 100 gig even from an electrical perspective. Maybe from an access side it makes sense, but not from us, not from the fabric side.
Right. And somebody going to go over the controller?
We are not specifically going over the controller. We want to go right to the DevOps stuff that Simon and Toad are doing. Unless you have questions on controller, we're happy to handle those.
Deal. Yeah, we'll shelf them for a beer.
What's that?
We'll shelf them for a beer later.
Perfect.
Oh, just one more question. Would it be possible to get the wiring diagrams for the PSI?
Yep. Yeah.
See that whole slide deck. Reference.
Absolutely,
no. Yeah, in the whole slide deck.
Yeah, and we haven't launched it officially. When we do, we'll have all documentation on it, and we'll provide that. But we'll give you what we have in the meantime. Absolutely.
Great.